Hello friends, welcome to HP Development Academy. In this particular lecture, we will discuss about the cyclic group. So let's start about discussion. So let us recall about discussion on the group. Okay, so let us recall about discussion on group. Okay, so we have a algebraic structure G star. Okay, so this algebraic structure is said to be a group if it satisfies four properties. Okay, four properties. Okay, so the first one is closure property. Second one is associativity. Third one is existence of identity. Fourth one is existence of inverse for each element. Okay, so when this algebraic structure is satisfying all the four properties, then we call this algebraic structure as group. Okay, so in closure property we have, suppose we have two elements a comma b. Okay, a comma b belongs to G. Then we have under operation this a star. So we have a star b belongs to G. Associative, let us take three elements a b c belongs to G. Then we have a star b star c is equal to a star b star c. Okay, existence of identity element, let us take an identity element E. Okay, so if we multiply this identity with any element, let us multiply this with E, then we get same element A. Okay, on multiplying the identity with any element, it will result into the same element. So A dot E is equal to A, this is equal to E dot A. Now we have existence of inverse. Okay, for each element belongs to G, we have a inverse. There exist A inverse belong to G such that we have A star A inverse is equal to identity. Okay, so for every element there must be an inverse. Okay, so if these four properties are being satisfied by this algebraic structure, then we call G as a group. G as a group under operation star. Okay, so under this operation star we have a group G. Okay, now this group G is called cyclic. Okay, so this group G is called cyclic if this group is being generated by a single element. Suppose this element A belongs to G. Okay, so this element is generating the whole group, then we call that group as a cyclic group. Okay, and we call this A as a generator. Okay, so A is the generator, this means A is generating the whole group, so A is equal to A is called generator of G. We will represent this like this. Okay, suppose B is generator of G, then we represent this as B is generating the whole group, then this is equal to G. Okay, so this is the basic concept of the cyclic group. Okay, and the representation is like this. Okay, so G is equal to a to the power n such that n belongs to positive integer. Okay, so we have G is equal to, let us consider this as a to the power square. Let us a square is a star. We have operated a two times with operation star. A star A, this is a square. Then we have a cube, this is three times of a star. A star A. Okay, we have operated a three times. Okay, like this, a to the power n. So n times operation, n times star operation. Okay, so we have G is equal to a square, a cube, a to the power n. Okay, so this is the this is group, cyclic group, and this A is generating this whole group. Okay, so by cyclic we mean that suppose we have the first element is A. Okay, now let us operate this one times. Okay, so this is A star A, this is A square. Similarly, A star A, this is A cube. Okay, similarly n times operation, n times, this is a to the power n. Now if we further operate this, a to the power n star a, then it will result into a. This means this is making a cyclic. Okay, this is making a cycle. Hence we call this group as a cyclic group, because these elements are making a cycle. These elements are arranged in such a way, it is making a cyclic. This is a to the power n, and further operation on a to the power n will result into the value of a. So this means this is generating a whole cycle. So that's why we call this as a cyclic group. Okay, now let us move further. Okay, so now let us go back to the definition of cyclic group. A group G is called cyclic if there exists an element A in G such that G is equal to a to the power n, such that n belongs to a positive integer. Okay, so such an element A is called generator of G. Okay, so we have the basic structure as G is equal to a to the power n such that n belongs to positive integer. Okay, so let us take the elements as, so we have G is equal to a, this is a star a. Okay, we have the algebraic structure as a G comma star, algebraic structure as G comma star. Okay, so this G forms a group under operation star. Okay, so we have, let us apply the operation. Okay, so now we have, let us operate this 3 times. So this is a star a star a. Okay, so a is operated 3 times, here a is operated 2 times. Similarly we have a is operated n times, Okay, so this we can write as G is equal to a square, this is a cube, similarly this is a to the power n. Okay, so this is the basic structure of the cyclic group. Okay, so if a is generating the whole group, then we called a as a generator. So this is equal to a is equal to G. A is generator of G. Okay, so if a square is generating the whole group, then we can write as a square. This is a square is the generator, so this is equal to G. Okay, so let us recall this. So why we call this as a cyclic? Because the elements are arranged in such a way that is, it is making a cycle. Okay, so we have the first element as a. Okay, so let us operate this 2 times. So this is a star a, this is a square. Now we have a cube, this is a star a star a. Okay, now let us operate this n times. So this is a to the power n. Okay, so the further operation with a result into the original element. Okay, so this is our a. Okay, so the elements are arranged in such a way that it is making a cycle. So that's why it is called a cyclic group. Okay, so now let us take some examples. So we have, this is Z. Okay, so these are the integers. Okay, so Z forms a group under addition. Okay, and this Z is a cyclic group. Okay, with 1 as minus 1 as generator. Okay, so how we can generate any element with 1? Let us generate Z plus with 1. Okay, so let us operate this. So 1 2 3 4. Okay, so if we want to generate 2, then we apply the addition 1 time. This is 1 plus 1. Okay, similarly we want to generate 3, then we have to add this 3 times, 1 plus 1 plus 1. Okay, this is 3 times operation on 1. This is 2 times operation on 1. Okay, similarly n is generated as n times operation, 1 plus 1, 1 plus 1 plus 1. This is n times operation. So 1 is generating this Z plus. So n belongs to Z plus, then 1 is the generator. Okay, similarly let us take negative integers. So we have minus 1, this is minus 2, minus 3, this is minus 4, this is minus n. Okay, so minus n belongs to z minus. Okay, so then minus 1 is the generator. Minus 1 is the generator. Okay, so for positive integer we have 1 as the generator. So suppose we want to generate minus 3. So minus 3 is equal to minus 1 plus minus 1 plus minus 1. This is operated 3 times. Okay, so minus 1 is generated, generating the whole set of negative integers. Okay, so we have z is group under addition with 1 and minus 1 as generator. Okay, let us move further. Okay, so let us discuss few more example. So let us take the example. We have Z5 under addition modulo 5. This is a group. Obviously, we have seen that ZP under addition modulo P is a group. Okay. Now we have Z8 under addition modulo 8. Okay. So now let us discuss this. Okay. So we have the elements in Z5 as Z5 is equal to 0 to n minus 1. So this is 0, 1, 2, up 3, 4. Okay. So let us try to generate this Z5 with these elements. Okay. So we have, if we operate 0 any number of times, then it result into 0. Okay, it will not generate any of these elements. Now let us operate 1 mod 5. So this is obviously 1. Let us operate 1 2 times. We are trying to generate Z5 with 1. Okay, let us write down here. Let us take these elements one by one. So 0 is not generating any of the element. Okay, so 0 is generating only 0. Okay, so this will not generate 0 is not generating, 0 is only generating 0. Okay, so this will not generate the whole group, so this is cancelled. Now let us take 1. Okay, so let us generate 1. Let us generate Z5 with 1. Let us generate Z5 with 1. Okay, so we have 1 mod 5 is equal to 1. Okay, now let us operate 1 2 times. So this is 1 plus 1 mod 5. This is 2. 1 plus 1 plus 1, 3 times operation with mod 5. This is 3. Now we have 1 plus 1 plus 1 plus 1. This is 4 times operation, mod 5. This is 4. Okay, so this is 1 2 3 4. Okay, now let us operate this 5 times. So this is 1 plus 1 plus 1 plus 1 plus 1 mod 5. Okay, so this is 5 mod 5. So this remainder is 0. Okay, so 1 0 1 2 3 4. So 1 is generating all the elements of Z5. This means 1 is generator of group, that is Z5. Okay, so 1 is generating all the elements of Z5. Now let us generate Z5 with 2. Let us generate Z5 with 2. Okay, so 1 is our generator. Okay, now let us generate Z5 with 2. So we have 2 mod 5. This is equal to 2. Now we have 2 plus 2 mod 5. This is equal to 4. Now we have 2 plus 2 plus 2. 3 times operation, mod 5. This is equal to, this is 6 mod 5. This means remainder will be 1. 6 mod 5. Na? This is 1. Okay. Now we have 2 plus 2 plus 2 plus 2 mod 5. Okay, so this is 8 mod 5. This means remainder is 3. Now let us operate this one more time. This is 2 plus 2 plus 2 plus 2 plus 2 mod 5. This is 10 mod 5. This means this is 0. So remainder is 0. So all the elements are generated. This is 1, this is 2, this is 3, this is 4, and this is 0. So 2 is also generating all the elements of Z5. So 2 is also a generator. So this is 1, this is 2. 2 is also a generator. So we have Z5 is equal to. Now let us generate Z5 with 3. Okay, let us generate Z5 with 3. So we have 3 mod 5. Okay, so this is equal to 3. 3 mod 5, the remainder is 3. Now we have 3 plus 3 mod 5. This is equal to, this is 6 mod 5. So the remainder is 1. Now we have 3 plus 3 plus 3 mod 5. This is 9 mod 5. This is 4. Okay. We have 3 plus 3 plus 3 plus 3 mod 5. This is 12 mod 5. This means remainder is 2. Now we have 3 plus 3 plus 3 plus 3 plus 3 mod 5. This is 15 mod 5. This means remainder is 0. So elements are 0, 1, 2, 3 and 4. This is equal to Z5. This means 3 is also generating Z5. So this is equal to 3. Now let us generate Z5 with 4. Okay. So we have 4 mod 5. This is equal to 4. Okay. Now we have 4 plus 4 mod 5. This is equal to 4 plus 4 is 8. 8 mod 5. The remainder is 3. Now we have 4 plus 4 plus 4 mod 5. Okay. So 3 times operation. Here it is 2 times operation. This is single time operation. Okay. So we have 12 mod 5. So remainder is 2. Now we have 4 plus 4 plus 4 plus 4 mod 5. Okay. So this is 16. 16 mod 5. This means remainder is 1. Okay. Now we have 4 plus 4 plus 4 plus 4 plus 4 mod 5. So this is 20 mod 5. The remainder is 0. So 4 is generating the element as 1, 2, 3, 4 and 0. So all the elements are being generated by 4. So 4 is also generating Z5. Okay, so 1, 2, 3, 4. So all the elements except 0 are generating Z5. So we have the generator as 1, 2, 3, 4. Okay. Okay, so let us find the generator of Z8. Okay. Okay, so we have the elements in Z8 as Z8 is equal to 0, 1, 2, 3, 4, 5, 6, 7. Okay, so let us try to generate the elements. Let us try to generate Z8 with all these elements. Okay, so 0 will not suffice the requirement because 0 will generate only 0. So 0 will not be able to generate rest of the elements. Let us generate Z8 with 1. So we have 1 mod 8 is equal to 1 mod 8 is equal to 1. Similarly, this is 1 plus 1, that is 2 mod 8. This is 2 mod 8. This is equal to 2. Similarly, 1 plus 1 plus 1. So we have 3 mod 8 is equal to 3. 4 mod 8. 4 mod 8. This is equal to 4. Similarly, 5 mod 8. It is equal to 5. This is 6 mod 8. This is equal to 6. Similarly, 7 mod 8. This is equal to 7. Similarly, 8 mod 8. This is equal to 0. So we have the elements at 0, 1, 2, 3, 4, 5, 6, 7. Okay. So 1 is generating all the elements of Z8. Okay. So 1 is generator. Now let us generate this with 2. Okay. So we have 2 mod 8 is equal to 2. Now we have 2 plus 2, that is 4 mod 8. 4 mod 8. This is equal to 4. Now we have 3 times 2 plus 2 plus 2, that is 6 mod 8. This is equal to 6. Now we have 2 plus 2 plus 2 plus 2. 4. This is 8. 8 mod 8. 8 mod 8 is 0. Okay. So this is, now we have, let us apply this further. So we have 2 plus 2 plus 2 plus 2 plus 2 mod 8. This is 5 times 2, na? 5 times. This is 10 mod 8. This is, remainder is 2. So this is getting repeated. This means 2 is not the generator. 2 is not the generator. Not the generator. Okay. So now let us, this is 2 is not the generator. Now let us apply this with 3. Okay. So 3 mod 8 is equal to 3. Now we have 3 plus 3, that is 6 mod 8. This is equal to 6. Okay. Now we have 3 plus 3 plus 3, that is 9 mod 8. This is 1. Remainder is 1. Now we have 3 4 times. 3 plus 3 plus 3 plus 3, 4 times. This is 12 mod 8. This is 4. Now we have 3 as 5 times. So 15 mod 8. Okay. This is 7. This is 1. This is 3. This is 4. This is 6. This is 7. So we are left with 5. Okay. So we have 3 plus 3. This is 5 times. Now, so let us apply this as 6 times. So we have 18 mod 8. This is 2. Okay. This is 5 times. 3 is applied 5 times. This is 3 is applied 6 times. Let us apply 3 7 times. This is 21 mod 8. Okay. So this is 5. So we have 1. This is 2. This is 3. This is 4. This is 5. This is 6. So 3 is generating all the elements. So this is 3. Similarly, we will check this. 4 is not the generator. 5 is the generator. Similarly, 7 is the generator. Okay. Let us compare this. In case of Z8 and Z5, let us compare this. Okay, so we have in Z5, all the elements except 0 are the generator. But in Z8, the generators are 1, 3, 5 and 7. So what is the concept here is that, let us write down the concept. So the generator of Z8 are, so Z8 is equal to, this is 1, this is 3, this is 5 and this is 7. Okay. So the concept here is that, so we have the group as ZP under, ZP forms a group under addition modulo P. Okay. So we have the cases as P is prime, P is equal to prime and P is not equal to prime. P is prime and P is not equal to prime. Okay. So when P is prime, all the elements except 0 is the generator. Okay. So we have P minus 1 generator. So elements in ZP is, element in ZP, let us write down here. So the element in ZP is 0, 1, 2 to P minus 1. So all the element except 0 are the generator. So generator are 1, this is 2, P minus 1 generator. Okay, but in case of non-prime, P is not prime. So here, if A is generator, then GCD of A comma P is equal to 1. Okay, so here in case of Z8, we have the P as 8, P is equal to 8. So GCD of A comma 8 must be equal to 1. all those elements that are co-prime to 8. Okay, so a is equal to all those elements that are co-prime with 8. Okay, so let us take the GCD with 8. Okay, so we have here the a will be, so the elements are in Z8, the elements are in Z8 elements are Z8 is equal to 0, 1, 2, 3, 4, 5, 6, 7, 0 to n minus 1. Okay, so let us take the GCD with a and 8. This must be equal to 1. So all those elements that are co-prime with 8 will be, a will be those elements that are co-prime with 8. Okay, so GCD of 0 and 8, this will not result into 1. So a will be those elements that are co-prime with 8. So these elements are 1, 2 will not be co-prime with 8. So this is 1, 1, 3, 4 will not be co-prime with 8. So we have 5. Similarly 6 and 8 GCD. This will not fetch into 1 because 2 as the divisor. Okay. So 6 will also not suffice the requirement. So this will 7. So the generator are 1 is equal to 3 is equal to 5 is equal to 7. So 1, 3, 5, 7 are the generator. Okay, but in case of the prime number Z5, all elements except 0 are the generator. This is the basic concept. So if P is prime, then the generators are P minus 1. So all elements except 0 are the generator. But in case of non-prime number, if A is the generator, then those elements that are co-prime with P are the generator. Okay, so suppose in case of Z8, P is equal to 8. So all those elements that are co-prime with 8 will be the generator. Okay, so those elements are 1, 3, 5 and 7 because GCD of all these number with 8 will be 1. Okay, so this is all about the cyclic group. Okay, so we will discuss further in next particular lecture. Thank you.